I'm J.U. Lee. I'm happy to present Eigen end-to-end resource optimization for large-scale databases on the cloud. In terms of the challenges we face, we believe there is no one-size-fits-all algorithm that can address everything. It's about finding the right balance between maximizing resource allocation and ensuring resource availability. Higher resource allocation increases the chances of allocation failure, particularly when idle resources are limited. On the other hand, high resource availability often leads in a lower resource allocation ratio. When it comes to serverless databases, there are some extra challenges that we have to consider. One is the frequent and dynamic workloads, as well as the need for timely allocation. Previous approaches primarily utilize two types of algorithm, best fit and worst fit. Best fit aims to fill a machine tightly, but may lead to failure for large requests and resource straining. Worst fit spreads tasks across all machines, but may require time-consuming migrations or adding new machines. Unfortunately, adding new machines instantaneously is not feasible for both scenarios, causing service providers often overestimating resource requirements and results in underutilized machines. So we present a hierarchical resource management system that treats resources as a dynamic flow. Our end-to-end approach aims to optimize resources from the user to the supplier. We ensure high availability and timely allocation so that online machines can effectively meet resource demands. But what about unpredictable spikes in resource allocation? To address this challenge, we have a buffer of warm machines that can be provisioned immediately so that it can handle unexpected spikes. We also consider cold machines in the context of supply chain costs. So our cascading resource flow model divides machines into 3 layers, addressing the challenges of each layer specifically. The online layer optimizes resources for non-empty nodes. The warm layer focuses on empty nodes, and the cold layer deals with offline nodes. To tackle all these challenges, we propose the adoption of an optimization algorithm at each layer. For the online layer, we leverage vectorized resource optimization, VRO. In the warm layer, we employ exponential smoothing with smoother adaptive margins. In the cold layer, we leverage machine learning algorithm, TCN. First, let's introduce online version of VRO. It aims to schedule resource requests on a minimum number of online machines. There are 2 challenges in the online bin packing. First, imbalanced resource dimensions, leading to stranded resources. Second, significant costs associated with cluster consolidation migrations. So we developed a 2-step best fit algorithm to address the 2 challenges. Step 1, we designed a loss-first heuristic, which essentially schedules a machine with the smallest residual capacity. But this still may produce suboptimal results. For example, showing on the right, the machine M1 has the smallest loss, but it may still be too skilled. To address this issue, we also introduce a skillness-first heuristic. Next, we utilize the skillness-first heuristic to minimize resource straining. We do this by first selecting candidate machines that meet the criteria of the Formula 1. After that, we pick the best machine by employing one of the three strategies. The diagonal direction policy, where we select the machine with the smallest theta. The bottleneck resource policy, where we prioritize machines with the largest bottleneck residual resources. The dot product policy, where we opt for the machine with the highest value of the dot product between the request vector and the residual resource vector. Offline version aims to address migration costs in offline cluster consolidation. Our approach consists of three main steps. Firstly, we use a cost-first heuristic to empty machines, focusing on those with the lowest migration costs. By doing this, we can efficiently clear out the machines and reduce overall costs. Secondly, we apply the online version to handle migration resource allocations. Finally, we carry out an instance exchange to complete the migration. However, there is a challenge. What is the optimal theta and how to find it out? So we use a binary search algorithm to identify the best theta. On the warm layer, we introduce ES with smoothed adaptive margins algorithm. It is a forecasting model specialized for short-term resource allocation. The model is designed to predict sharp spikes better than traditional time series methods. It also enhances ES predictions by incorporating a smoothed adaptive margin that adjusts rapidly and decreases smoothly based on second-order derivatives. For long-term time series forecasting, we utilize machine learning algorithm TCN and implement a minimum stock policy. Let's talk about experiments. In the online layer, we conduct the evaluations of the VRO algorithm in different scenarios: online, offline, with and without instance exchange. These evaluations are shown on the right. We also compared the performance of VRO with several baseline algorithms, including first fee, best fee, and Kubernetes policies like most allocated and request to capacity ratio. As you can see in the figure below, VRO outperformed all of the baseline algorithms in terms of bin packing efficiency. As you can see, the graded bin packed numbers, which represent the results of VRO, were higher than those of the baseline algorithms. In particular, when the policy of instance exchange was implemented, as shown by the red dot box, the bottleneck policy demonstrated the highest level of bin packing efficiency among all of the VRO policies. In the warm layer, ES with smoothed adaptive margins successfully tackles 5 spikes, as shown on the figure, A, B, C, D points, and 1 quick decrease at point E. It also outperforms other ES variants by significantly reducing the insufficient resource events. Moreover, it just comes with only a minimum cost increase. In the code layer, TCN manages offline machines by adding them before allocation increases and removes them before it decreases. It shows in greater accuracy during decreasing allocation compared to base stock policy. In terms of costs and the reduction of insufficient resource days, it also outperforms the base stock policy. Finally, end-to-end evaluation. Both online and web machines and total machines are proactively adjusted before the actual allocated memory changes. Compared to the original total machines, Eigen significantly decreases stranded resources. On average, the allocation ratio is improved to 87%, and the utilization ratio is improved to 61%. No request failed due to insufficient resource provision before and after Eigen. To summarize, Eigen significantly improved resource allocation with a little rise of failed requests. Conclusions. Eigen implements a hierarchical resource management system with 3 resource optimization algorithms to achieve comprehensive resource optimizations. The evaluation of Eigen demonstrates a substantial enhancement in resource allocation ratio while maintaining high resource availability.